Hey everyone, in the next few minutes, we are going to do a quick demo on our machine learning group project. So our project topic is the handwritten digit recognition. Our goal is to apply different machine learning algorithms to see how well they can classify handwritten digits. To compare the performance of different classifiers, we consider both accuracy and efficiency. To evaluate the accuracy, we have generated a confusion matrix and computed their corresponding precision, recall, and F1 score. To evaluate the efficiency, we have used the time package in Python to calculate the testing time and training time for each classifier. And so far, we have tried 6 different machine learning methods, including KN, PCA, logistic regression, decision tree classification, random forest, and feed-forward neural network. So the data source we have used is the MNIST database. It has 60,000 training images and 10,000 testing images. Each image contains 784 pixels. In other words, there are 784 features in one target. Since the original dataset is in IDX5 format, we have self-written a data parser in Python. So here's a plot of a digit 5 from the original dataset, which demonstrates we have successfully parsed data into our workspace. And before we start applying machine learning algorithms, we analyze the distribution of training target. As you can see from the bar chart, they're very evenly distributed, and digit 1 has the most cons. So it could be our default target when we do a blind guess. And this way, the error rate would be around 88%, which is pretty large. So the first method we have tried is the k-nearest neighbor classifier. Since the training data has a very high dimension, it takes lots of time to train a KN model and it predicts the results. It turns out that the k equals to 1 works best. Though KN gave us a pretty low error rate of 0.031, we will not consider using this method directly because it's very time-consuming. So the next thing we have tried is to reduce the number of training data. We have tried sampling the data into a size of 100, 500, 1,000, and 5,000. It's obvious to tell that less training data costs less time to train and predict, but it outputs a lower accuracy. The following graph shows the normalized confusion matrix for KN, which is plotted using the heat map in Seaborn package. So as you can see, even there 5,000 data, it still produces a lower accuracy compared to the standard KN. So it is not a good choice to reduce the number of data. What else can we try is to reduce the dimension of data. Principal component analysis, which is PCA in short, does a good job on that. It's a linear transformation method by projecting the data into lower dimensions and maximizing the variance in data. We have found that when the PCA has 25 components, it gives out both a large variance in data and a high KN test score. So after we feed the KN classifier with the reduced features and k equals to 1, we surprisingly found that this method has a very high testing accuracy and significantly reduces the training time and testing time at the same time.
I will explain how decision tree and random forest work in digit recognition in our project. First, we set the max steps of decision tree to default, which means that all the nodes are expanded until leaves are pure. And it is a fast approach, but with a low accuracy of 87%, which is much lower than other algorithms in our projects. And the decision tree is poorly classifying digits 5 and 8. From the confusion matrix, you can see that they have a relative low accuracy rate. So it is intuitive to think of random forest, which is putting many decision trees within a forest. And when all the decision trees give classification results, it's averaging all the results, so it can both decrease the bias and variance in classification. We have tried from 10 trees to 200 trees in the forest, and the best estimator we get is 200 trees in the forest. The training time is not slow. It takes about 20 seconds to train the model, and it shows a relative high accuracy rate, about 97%. And from the confusion matrix, you can see it performs averagely on every digit.
So, in addition to the previous classifiers that we learned from class, we also try to stretch our project a bit further by including a feed for neural networks. And the feed forward neural networks is actually the simplest form of the neural networks, but it do achieve relatively high performance. And with our model, we include only one hidden layer and set our learning rates relatively high to reduce the training time, but we do achieve the overall like 97% of accuracy. And uh, and I think with further tuning of the layer size and the learning rate, we can actually achieve better results. But overall, we are pretty satisfied by this outcome. So here, let's look at the overall comparison between all the models that we talked about in this project. As we can see here, the principal component analysis plus KNN actually won the title by quite a margin. It has one of the highest accuracy and the lowest training time and also the test time. I think this is because of the principal component analysis greatly reduce the features size. Actually, for all the other models, we directly apply each individual pixels as the feature. So this actually is not very efficient and can introduce noises and other errors. So I think this is all the information in our for our project. Thanks for watching.